Hello everyone, my name is Hüseyin. Today we will be talking about operating system. This is eighth week of our course. First, I will discuss the objective and function of operating systems. Then I will explain the concept of scheduling and memory management. Finally, I will describe how memory management is implemented in modern systems, especially Pentium memory and IRM memory. An operating system is the main software that manages a computer's hardware and software resources and provides a safe and easy way for program and user to interact with the computer. It has two. It has two main goals. For convenience, the operating systems make the computer easier and more user-friendly to use. Second, efficiency. It ensures that the computer's resources are used in most effective way. Without an operating system, the user would have to manage all hardware and software resources manually, including CPU scheduling, memory allocation, input and output operation, file management, error handling, and resource sharing. Operating systems provide service in several main areas. They help us create programs by giving them the resource they need and getting them ready to run. They manage running programs by loading them into memory and sharing CPU time. They let programs safely use input and output device. They also control access to files so only allowed users can open and change them. They manage who can use the system and protect resources. They check for errors and fix programs to keep the system stable. Finally, they keep track of how resources are used to help monitor performance. Now, let's take a look types of operating systems. On slides, the first four types are classical and historical operating systems. These are early designs that laid the foundation for modern operating systems. The second group includes more modern and advanced operating systems. They incorporate features like multitasking, virtual memory, and improved user interface, which make them suitable for today's desktops, server, and mobile device. First of all, early systems. No operating systems existed. Users interact directly with the CPU and hardware. Programs were loaded and executed manually. This was simple but inefficient and error-prone. Second systems, the simple batch systems, jobs were processed in batches. User had no direct access to the CPU. A monitor controlled job sequence and managed execution. Job control language was used to define job instruction. This improved CPU utilization and reduced idle time compared to early systems. The third one is multi-programming systems. Multiple jobs are kept in memory simultaneously, and this brings us to main reason why we need such memory management. Input and output weights are overlapped with the other jobs. This method increases efficiency and reduces CPU idle time. Third one, the time sharing systems. Multiple users interact with the systems at the same time. CPU time is divided into small slices shared among users. Each user feels the system's response. The modern operating systems. Real-time operating systems designed for applications require guaranteed timing used in embedded systems, robotics, medical devices, and industrial control. Distributed operating systems manage a group of computers as a single system. Users may not know which physical machines execute their program. Network operating systems focus on managing network systems, provide file sharing, printer access, common in office, local area network environments. Last one, mobile operating systems designed for smartphone, tablets, and wearable devices, optimized for power management, touch interface, and connectivity. Example, Android and iOS. Before we discuss scheduling, let's understand what a process is. A process is a running instance of a program. The operating system keeps track of all important information about each process in a process control block. This includes the identifier, process state, program counter, CPU register, priority, and input and output status. Schedulers use information stored in the process control block to decide which process should run next on the CPU. Scheduling is the process used by operating systems to decide the order in which process get to use the CPU. Its main goal is to use the CPU efficiently and keep all processes progressively fairly. There are three main types of scheduling: long-term, medium-term, and short-term scheduling. Long-term scheduling decides which processes are admitted into the system from the job pool. It controls the degrees of multiprogramming. Medium-term scheduling temporarily suspends or resumes process to balance CPU and input and output loads. Short-term scheduling, also known as a dispatcher, decides which process in memory will use the CPU next. It happens very frequently and focuses on keeping the systems responsive. As you can see the figure, this shows how an operating system works when multiple programs run at the same time. When a process needs something like opening and reading a file, the service will handler takes care of it. If an interrupt happens, like a timer ending or input and output phishing or some hardware event, the CPU pauses and the interrupt handler handles it. New jobs are waiting to start go into long-term queue while ready process go into short-time queue. The short-time scheduler decides which process gets the CPU next. Process doing input and output move to input and output queue and come back when done. This way, the CPU stay busy and multiple jobs run together, and CPU and input and output resource are used efficiently. Now, we will talk about memory management in operating system. Basically, systems can be divided into uniprogramming and multiprogramming. In both types, a part of memory is reserved for the operating system, called the resident monitor, while the rest is available for the user programs. In uniprogramming systems, only one program runs at a time. Most, most of the time, the CPU is idle because the program may be waiting for input and output module. Examples of uniprogramming systems include simple batch and MS-DOS. If user program is too large to fit into memory, a method called overlay is used. The program is divided into modules and only the needed module is loaded into the memory. In older systems, program could also be manually designed to fit the memory size. In multi-programming systems, the operating systems dynamically manage the memory. This keeps the CPU busy and allows larger programs to run without overlays. Techniques used include swapping, part partitioning, paging, virtual memory, and segmentation. In operating systems, we have different queues to manage process. The long-term queue and the short-term queue and input and output queue. The long-term schedules brings the process from disk into memory. The short-term schedules decides which ready process get the CPU next. This helps the CPU work more efficiently than in uniprogramming system. But this is still not enough. The CPU is much faster than input and output device, so sometimes all processes in memory are waiting for input and output device, and the CPU stays idle. One idea is to make the memory bigger, but that doesn't really help because bigger memory usually means bigger programs, not more programs. And the fourth solution is the swapping. The operating system can move a process from memory to disk temporarily and bring in another process to run. This way, the CPU keeps working even if some processes are waiting for input and output, and the system can handle more processes than memory alone allows. Next slide, we will talk partition that second method, memory management. Another memory management method for CPU is partitioning. Memory is divided in partition, but they are not always equal because each process may need a different amount of space. We can example of equally sized and different size partition in the image on the left. But different size partition don't give a full solution. For example, if we have 4 MB of the memory and place a 3 MB process, a small empty space remains. Partition can be fixed or dynamic to reduce wasted space. Sometimes swapping is used together with partitioning to fit more process into memory. This method helps the operating systems use memory more efficiently. Now, after swapping and partitioning, we can use paging to make memory use more efficient. We split a process into small parts called pages, and memory itself is split into equal size frame. Each page of a process goes into a free frame. The operating system keeps the tracks of which page is in which frame using a page table. This way, we can fit more process in the memory and keep the CPU busy. With paging, a process can be loaded into memory even if free space are not next to each other. With paging, it was realized that an entire process does not need to reside in a memory. Only the pages that are actually needed are loaded. This led to development of virtual memory, which allows the operating systems to manage processes larger than the available physical memory. The disk acts as a temporary storage area, and operating systems keep track of which pages are required and when. Using demand paging, the operating systems bring a page from disk into memory only when it is needed. This ensures that the CPU always has the required page ready, maximizing efficiency and allowing more processes to run concurrently. In virtual memory systems, the CPU uses virtual addresses to read data. This virtual address must be translated into a physical address. Normally, The CPU would first go to memory to find the page table entry, and then go to memory again to get actual data. This means two memory access for every operation, which is very slow. To fix this, we use a transaction look-aside buffer, or TLB. The TLB is a small, very fast cache that stores the most recently used page table entries. When the CPU needs an address, it first checks the TLB. If the entry is there, CPU can immediately get the physical address without accessing memory. If the entry is not there, only then does the system check the page table in memory. Because programs usually reuse the same page, most lookups are found in TLB, and this makes memory access much faster. Last method is segmentation. Segmentation is a way of dividing memory into variable size block called segment. Unlike paging, segments are visible to programmer and make it easier to organize program and data. Each segment can have its own access rights and can grow or shrink as needed. Segmentation also allows sharing code or data between process and provide protection. Some systems even combine segmentation with paging to get benefit of both methods. And now we talk about memory management, how to implement modern system. First of all, Pentium memory management. Pentium systems are commonly used in desktop computer, network system, and workplace. They manage memory using segmentation and paging. Both mechanisms can be optionally disabled. It means the user or programmer, if they want, they can close one of them or both of them. The memory access process occurs in three stages. First of all, segmentation. The program generates a logical address which consists of a segment number and an offset. The segment number is to use look up the segment base address and limit the segment table. The offset indicates the distance from the segment starting address. The CPU combines the segment base address with the offset to form the linear address. Second stage, paging. The linear address is translated into a physical address using the page directory and page table. The page directory uses the upper bit of the linear address to select the appropriate page table. The page table uses the middle bits of the linear address to find the corresponding physical memory frame. The third stage, main memory access. Once the physical address is obtained, the CPU can read and write data in RAM. Although segmentation and paging add extra step, the CPU uses TLB to cache recently used address translation, minimizing performance impact. In summary, in Pentium systems, memory translation follows the path: logical, linear, and physical address. Segmentation hence logical organization, while paging manages physical memory access. The TLB ensures that these extra steps do not significantly reduce performance. Let's talk about IRM memory management. First, IRM does not use segmentation like Pentium. Instead, it uses a flat memory model, which means program can generally treat logical address as a linear or physical address directly. This makes memory access simpler and faster. Second, a modern IRM processor includes a Memory Management Unit or MMU. The MMU has several important jobs. First, it translates address converting linear virtual addresses into physical address. Second, it provides memory protection so that program can only access their own memory. If a program tries to access memory it shouldn't, the MMU triggers a fault. Third one, it supports virtual memory, which allows the system to use more memory than physically available by swapping unused pages to disk. Finally, to keep performance high, it uses TLB, which cache recent address translations, so the CPU can access memory quickly. When paging is enabled, the MMU translates a linear address through the page table into physical address. However, in simple embedded or low-power IRM systems, paging is often not used, and CPU accesses physical memory directly. The operating systems play a role if paging is active. It manages the page table and enforces memory protection. In simpler systems, the operating systems may work directly with physical memory and MMU might be turned off or used minimally. So, to summarize, IRM systems are simple, energy efficient, and ideal for mobile and embedded devices. The flat memory model makes addressing fast, and MMU, when present, provides translation, protection, and virtual memory. In embedded systems, the MMU can be minimal, allowing direct access to physical memory. Last one, if we want to compare Pentium system and ARM memory management. In terms of memory management, Pentium segmentation and paging, flexible but complex systems, IRM flat memory model and using MMU, optional paging and simpler and faster. In terms of power consumption, Pentium systems high because designed for desktop and servers. IRM power consumption is low, optimized for mobile and embedded device. About software ecosystems, Pentium very extensive, supports a wide range of desktop and server applications. IRM focused on embedded, mobile, and smaller ecosystems. In terms of architectural complexity, Pentium systems is high, supports advanced features like segmentation, virtual memory, multiple privilege level, and IRM architectural complexity is low, simpler architecture with fewer features, easier to implement and maintain. The last one, the performance focus, Pentium systems, high performance computing, multitasking, and virtualizing, and IRM energy efficient performance, good for real-time and battery-powered application. Thank you for listening.